Good afternoon, everybody. I want to introduce my research paper. The title of my research paper is Active Surface for Fully 3D Automatic Segmentation. My name is Albert Comelli. I am a scientist in biological images processing and analysis at the Perimeter Foundation. I am a research affiliate at the Laboratory of Computational Computer Vision in the School of Electrical and Computer Engineering at Georgia Tech Institute of Technology. Positron Emission Tomography is a crucial methodology towards precise radiation therapy treatment planning, also to identify the most aggressive areas within the tumor. Radiomics is an innovative and promising biomedical approach aiming to provide quantitative information for biomedical images. Radiomics future extraction from PET imaging depend on the reliable tumor volume segmentation. In our recent study, we devised an algorithm for semi-automatic tumor segmentation that becomes full automatic in the case of brain lesions. The present system inherits several features from the system described in our previous work. In previous work, the first step was the automatic identification of the optimal starting 2D mask surrounding the tumor using the regional grooving method. This mask was used as input for the subsequent step of the system, where the segmentation process was performed combining a local region-based active contour algorithm appropriately modified to support PET images. The obtained mask was then propagated to the adjacent slice using a slice-by-slice meshing approach. Propagation was performed in parallel both upward and downward until a suitable stop condition was met. Finally, a user-independent three-dimensional volume was obtained. The present system inherits the same pre-segmentation design, while the fine segmentation is achieved, evolving one whole active surface which intersects and segments all PET slices at once, replacing the slicing mesh active contour. To obtain a full automatic segmentation, the initial 3D mask enclosing the tumor must be obtained without any operator intervention. Consequently, the system identifies the PET slice containing the maximum SUV in the whole PET volume by taking advantage of the great sensitivity and the specificity of the MIT radiotracer in the discrimination between health and the tumor tissues. Once the current slice with maximum SUV has been identified and automatic procedure identifies the mask surrounding the tumor, the voxel containing the maximum SUV is used as a target seed for raw 2D segmentation based on the region grooving method. Starting from the two raw segmentation, the major axes of the contour are used to obtain an ellipsoid which contains the tumor. This 3D shape is fed into the next logical block of the system, where the delineation takes place through the full 3D active surface methodology. The ellipsoid is used as input and evolving to minimize the energy E and consequently to fit the tumor silhouettes. Also, we reformulate the energy function to work efficiently in the 3D space. To assess the performance of the implemented 3D system, 10 clinical cases of oncology patients with brain metastasis were considered. We compared the gold standard with the contour obtained by intersecting the active surface with the planes defined by the PET slices. For each clinical case, we computed the score and the Hausdorff distance, and we compared them with the corresponding result of the previous study. An example showing the difference between the segmentation based on active surface and the slice matching approaches proposed. In A segmentation based on slice matching, red contour and the gold standard yellow contour are superimposed. Surfaces are rendered with a certain degree of transparency to emphasize volume intersections. In the same way, the proposed active surface segmentation, green contours, and the gold standard yellow contours are shown in B. In this study, we upgrade our previous 2D system based on active contour and slide matching to full 3D system based on active surface. The present study describes a 3D shape evolution capable of segmenting the PET slices all at once and therefore capable of leveraging additional cross-slice information that was not used at all before. Second, a significant benefit of the 3D active surface over the 2D slice matching approach is that it does not require any stopping condition, as the tumor boundaries are naturally managed in the vertical direction as well. Third, the present paper aims to demonstrate the improvement performance obtained in migration the system from 2D to 3D. Thank you for your attention.